Live. Yeah, hello. This is the second episode of Meeting C++ Live with today my guest, Joel Falcou, and we're going to talk a bit about C++ 11 and 14 code generation. That's something I saw at Embo C++ talk from Joel. And so, hello, Joel.
Hey, gents. How are you?
I'm fine. A bit excited about the second episode and if everything is working.
Great.
So, Joel, could you introduce yourself?
Oh yeah, sure. So I'm Joel Falcou. Well, I'm I'm an assistant professor somewhere near Paris in France, where I teach and do research about C++. And I also happen to be the CTO of a startup called NumScale, which deal with high performance computing tools and stuff like that using let's say, bleeding edge C++. So I've been around the C++ community for quite a while now. I've been involved in Boost mostly and the community in general. I'm running the one of the French C++ user group meetup located in Paris, and well, I try to be involved in C++ in general whenever I can.
Okay. Yeah, I noticed you're pretty active in that area. I still
I
have to
try.
make it to Paris to speak at your meetup, but
Yep.
you have been for several years now a speaker at my conference, but also at C++ Now and CPPCon. And as far as I know, you're also very much involved with Boost SIMD, so
Yes.
the SIMD library's parallelism on the processor itself. That's pretty
Yes.
cool. And today we're going to talk about one of the techniques you're using to make that possible, I think, right?
Yep. It's
Um,
yeah. We when we started dealing with the implementation of both SIMD, one thing was actually very clear is that the we needed tools and new way to be sure that the compiler, or more specifically the compilers, all of them, were actually playing nice with the kind of code we wanted to generate. So basically, when you are dealing with code at the level of SIMD instructions, let's say that a single instruction misplaced or misgenerated means that your speed up just crumbled down. So we wanted to have a way to write codes that are able to sustain this level of performance everywhere, and
mhm.
we found out that you cannot just let the compiler try to do whatever he wants to do, because sometimes he just apply um, generic regular code generation rules that are far okay for regular codes that just blow yourself up. And now what we wanted to do was to actually manage to control that. So
Mhm.
we obviously turned around to metaprogramming. So metaprogramming help us to actually specify what we want to generate, and we let the compiler follow those new rules, so we know that we get what we got. And for a long time, C++ metaprogramming was a bit, let's say in well, some kind of disarray. There were a lot of
Yeah.
techniques, but they were all looking more like acts than anything else. And C++ 11 actually um, cleaned up a lot of this
Mhm.
by standardizing stuff like variadics templates, and it opened an area where um, dealing with this kind of codes where started to look like something you can do in regular C++, and nobody will actually look at you strangely because you write more angry brackets than anything else.
Yeah.
So it helps the techniques to become more, let's say, mainstream or something. And it happens that C++14 continued into this direction by adding more and more support for things that are not actually and solely for the purpose of metaprogramming. That's where I think
Mhm.
the um, the the elegance of it is. It's features that help you doing a lot of things, So I'm mostly speaking about, for example, polymorphic lambda functions that let you write a lambda function with let's say a template arguments,
Yeah.
and
You
we have
can you
that.
can you can use auto in the
Yeah,
parameter
yeah.
list
You just
of
happen to use
lambdas with
auto.
C++14,
Yeah, yeah. So you can have
which
auto parameters in lambdas. You can actually use lambda as, let's say, a box containing a piece of code, and this code being parameterized by these polymorphic parameters, you can carry it around until the point where you need it, and then you call it, and the compiler is about to generate the code for. And so validate templates, polymorphic lambdas. Constexpr is also
yeah.
a big new player. It was okay in C++11. I think it was restricted to a very, very small list of cases, mostly because I think people from the compiler weren't sure we can do better than that. And C++14 actually made it, well, quite generic. You can have for loops or whatever in your
Mm.
context for functions, and that's quite cool because you could actually write a function that you want to call at runtime because it do something interesting, and you can call it at compile time, let's say, or let's say in the compile time context, okay, and you get the same stuff run at compile time. And by the fact that you can use the most generic way to write your function, including loops and whatnot, you're sure that the performances of the runtime is not, limited by the fact you have to write it in a specific way for the compile time.
Yes. So um, let's just directly step into this. You're
Yep.
talking a lot about code generation and the techniques how you write your code, which then is basically in a generic way expanding into the code generation that you need through specializations, etc.
Yep.
So in your talk, you first gave like a little short introduction into TMP, which I'm gonna switch. So I'm just directly gonna switch to slide 7,
Yeah. Let's go to the
where
meat.
we get the just so for you, this is new idea is that you use variadics as a code replicator and computation via constant expression, because that's now actually more usable in C++14, and
Yes.
lambdas are also, for you, like as a customization point from the outside, but also they're usable with C++14 and, in a generic context much
Yep.
more. And
Yep. So more to the point, we started experimenting with this in a lot of different contexts. What happened was we needed to have a way to say, okay, this is a piece of code. This is the most simple piece of code I can actually need to generate,
yeah,
and we wanted to be able to say, okay, this piece of code, okay, for this kind of function, this is the one we want, and for this function, which is exactly the same except for that, this is what we want, and so on and so on. And we came out with this idea of having lambdas as I say, as a representation of a code fragment.
yeah,
And by relying on this, we can actually have a very generic code generator just parameterized by the lambda. But then, at some point, the next stuff you want to do, and so I don't know who is actually watching, but I'm actually anticipating the question is a lot of things we do and that we will be doing there are now far more simple using C++17. But we were in a context where going to C++11 and 14 was already a big move. So we wanted
yes,
to have something that works within these constraints. So we found out that the one thing you want to metaprogram quite a lot is I have a statement that do something depending on an index or a type in a list of type, and I want to unroll, let's say, this statement for every value or every types in the type list.
mm,
And the classical way to do this was, okay, you just put it into a box, and you use template structure specialization to unroll the count, all the types, and so on
Okay,
and so
yeah.
on. And it was looking bad. It was looking bad because we were needing to write those box all the time, even if they were looking all the same, and so on and so on. And that's where using the variadic pack expansion came to our attention. So the
Yeah.
basic idea is to say whatever you.
Let's
Oh,
move forward into
oh yeah.
that, into variadic templates, because that's
Okay.
actually one thing we had some trouble understanding, and that's actually a point where you kind of so we see this slide now. Just quick, run over variadic templates. You have like a parameter pack as type name dot dot dot.
Yep.
And if you then just give it a name after that, in this case it's like just a T, and if you then say this name dot dot dot, that is the pack expansion, and you can apply that to parameters and also to lambda parameters. And with C++17, I think we also get variadic lambdas, which will again, be a bit probably adding more things into this or making things easier,
I,
maybe.
I think you have variadic lambda already in 14 actually.
That could be true. Something else was lambdas in 17.
If I remember correctly, because I think we used the trick at some point. So
Okay.
Yeah, we can play around after that.
Well, if you already have variadic lambdas, that's cool.
Yeah.
But then this is just the first example, which I also find kind of confusing. But that's just how you can derive types from parameter packs. So on slide 10, you say turtles all the way down. So basically, if you want compilation speed, which we are kind of interested in C++, with variadic templates, we have to replace recursion, which basically when you start working with variadic templates, recursion is so easy to achieve, and it's easy to understandable because it's a concept which is always already familiar with most of us, and it's just like one of the first things you learn. And we don't really have like a loop structure to put this into an iterative way.
Yeah.
And then you say you turn it into code that can be comma separated.
Yes.
And this sounds so logical, like, oh yeah, let's just code comma separated. But actually, how does that work? And that took me quite a while to understand. And that's why I just prepared a small example where I think we just could walk over and see how we turn a recursive version into this comma separated version, which comma separated sounds a lot more complicated than it actually is once you know the trick. So I'm gonna switch views, and that's our example, which basically is just how you add some arguments up from a pack. So basically you get the sum of the pack, and that's just an example. And in the first half you see oh wait, 1 second. So one thing at the beginning I didn't understood if I still need this this base function, which basically is the zero case in the recursive way. But in the way when we do comma separated, we don't need that. So our code is already shorter.
Yeah.
And so in the recursive way, you have this kind of as the null case for when we expanded everything. Otherwise, we get a compilation error. So we always have to provide this kind of special function handling this corner case. And then we recurse and say first plus recursive sum. So we call ourselves again. And you might want to forward your arguments or not. Just in this case, I'm just lazy and just doing it in this case. And also, yeah, you might want to make this like some reference or not. But in this case, it's just as an example.
Yeah.
And this is the basic code which I think a lot of people have in their code base today, where they're just using variadic templates and using recursion because it's easy. And what I find interesting is that actually for the compiler, that's not such a good thing to do.
Well, the thing is that at some point, even if at the end your code will be probably completely, optimized and compressed. The compiler has to know what is the symbol of the next recursive sum function to call. So you call one with, let's say, 6 floats, and so you match it against the one with 1 float first and then a pack of 5. And then you call it on the pack of 5, which means it has to generate the symbol for the function with a pack of 5. That we will map on 1 plus a pack of 4, and so on and so on. And so you will end up with all these intermediate symbols that needs to be, found out, because when the compiler tries to find the proper overload function for the next recursive sum steps, it basically go all over around onto, okay, which function recursive sum should I call? And this costs because it has to find it has to resolve the overloads. Maybe the symbol name itself has to be built and mangled so it can be compared to something else. So it involves a lot of, how to say that, a lot of bookkeeping for pretty much nothing, because at the end, when the optimizer will roll over that, you will end up with a code which is equivalent to return value 0 plus value 1 plus value 2 plus value 3 and so on and so on. So everything disappears, but you spend time, compile time, to actually
the
know
compiler
about them.
basically has to create a function instantiation for every call to the recursive function.
Yeah.
So if you have a list of 4 elements being added, it's gonna be creating 4 different functions from 4 to 3 to 1, etc.
Yeah.
And only the first one you already given to the compiler because it cannot do that automatically.
Yeah. One way to see that, I did the experiment a bunch of time, is you take this kind of code and you compile it into, compiler explorer, and you turn off optimization.
I did play around with that too.
Okay,
that's so actually very interesting to do.
Yeah, and so if you turn off optimization, you see that all the symbol from, like a recursive sum with 1, with 2, with 3, with 4, and so on, appears in the binary. Even if at the end the one you call from the main function is optimized. So that means that at some point the compiler is doing this, this mental exercise to know which is the next function I need to call, resolve it as a full-blown function, and continue over that. And it involves a cost. It's not free. I mean, it has to do all of this. So if you have 5 or, I don't know, 4, 6, I don't know, a few numbers of parameters, it's okay. But what happens if you start having, I don't know, like a dozen or 20 or something? So one can argue that if you have a recursive sum of 25 or, I don't know, 100 parameters like this, you have other issues like design issues, but it may happen. And in our cases, on some compilers, sometimes what happens is that if you do it with 1, 2, 3, it's okay. And for some reasons, well, 4 is out of question. Like I'm not going, to optimize past 3 because reasons. So we wanted to have a way that was, let's say, compiler savvy, that ensures that everything get in line, whatever the number of stuff we deal with. And so
that's where the second, the comma separated solution, or the comma driven solution, which we see here, comes in. And for a long time, it sounds so easy to it's just a comma in, but for a long time I quite didn't really cope how this works. But basically, this is like the biggest hack in C++ 14 for TMP, I think.
Yeah.
So you kind of abuse an initializer list, and if you have a comma operator, then only the last thing is being evaluated. So you can put, like an expression in front of this,
Yeah.
which in this case is used to add up the sum.
Yep.
And then again, for a second time, we abuse the comma operator to make this in one statement to return init after it's added to everything. So this
Yeah.
is kind of like a do-while loop at
Yeah.
compile time.
It's a do while over the argument pack, let's say.
Yeah.
And as you say, the keyword is abuse. Okay. It's like someone actually took all the lawyer-esque pages from the standard and say, okay, if I combine this and this, it's all legal. But what we do is we know that if you put something on the left of operator dot dot dot, and if these things contains something which is an argument pack of types or values, whatever, it will iterate over all the elements in the pack and put a comma in between all of them. And if you look at the standards, you know that you have a very few places where you are allowed to do this. The first one is obviously function parameters. And the other one is whenever you want to initialize something
Yeah.
in between curly braces. So what we do there with initializer list could also be done with, like for example, a local table of rule or something that you instantiate something. So we say, okay, let's be in a comma savvy context. So let's it be the constructor for initializer list. So what do I want to do now? I want to repeatedly call something that contains my my argument pack.
Yeah.
So there, what we want to do is a sum. So we
But
start by saying, okay, let's do the sum.
yeah. But if we switch back to your slides,
Yes.
when we have now seen the code, you also have an example for that in your slides.
Yeah.
And you also show that it actually gets so this is your example, which
Okay.
also uses an std array. And if we go to C++ 17, actually the code becomes
Yeah.
this. It's much
It's
cleaner and much easier. And
yeah.
you this is called fold expressions.
Yes.
And
That's probably the next best thing coming in C++ 17.
so the whole and this is gonna make this technique a lot cleaner.
Oh yeah.
But on the end user is probably never gonna see this, as this is supposed to be in implementations in the background.
Yeah.
And
It's typically one of these features that are like I think it's targeted more to a library developer than actual application level code writer. But it's cool that we can actually do this in a non completely screwed way.
oh yeah.
Yeah.
And now
And so
yeah.
and so just on this example using C++ 17, it's now possible to actually write a generic unroll statement function. So you can shove your statement into a lambda. You make your lambda take a polymorphic parameters,
Yeah,
which
let's
will
move
be
to lambdas. That's a good idea.
yeah.
So in your slide set now, the next point of those 3 points is
Yeah.
lambdas, which are like really changing the way you use C++ once you're used to regularly using them.
Yeah.
And so the one thing you marked red on this slide is enable higher order programming.
Yes.
So
so higher order programming is the fact that you can write function that can manipulate function as parameters or as results. So you basically turn a function into a first class value based type. And
Okay.
when you start thinking about having functions as a regular value, a lot of things open up. So it's not something which is actually more, C++ than anything else. It actually stems from all these, functional programming languages that predate C++ by probably decades.
Yeah.
And these examples is what I think is the most important thing that shows that you can now reason around functions like you could before with values, and which actually adds value to the code base you're writing. So it's a good old jokes about I need to make a functions that take two functions and return me the composition of them. And if you wanted to do that before, it was messy. That was basically trying to combine steady bind with steady binds and do
Yeah. Oh
things
yeah.
like this. So you see, it can get messy. So now it's actually rather straightforward. I have a
Yeah.
function takes function. So let's
So
just take arbitrary parameters because function types there are many of them. And if you do this, what do? I need to return something that looks like a function. Good deal. That's exactly what a lambda function is.
mm, yeah,
Um,
that's so this makes functional programming in C++ a lot easier, and
oh yeah,
lambdas
yeah. It's not even easier.
are a
It's
big
actually
enabler
usable.
for a lot of things and innovations we've seen the
Yeah.
last years. Um, so let's skip that slide. Okay, so I see. So in the next two slides, you show how to use enable if
Yeah.
to simply call a selected function or the type itself, right?
Yeah.
And then use for each on some container and use the select template and use like is trivial to see if the type itself is like is it trivial or not. And in the case that it's trivial, you do nothing, and in the
Yeah.
other case, you insert a
Yeah.
lambda, which
I'm calling construct on the element, and
yeah,
a is supposed to be some kind of allocator or something.
and yeah, so
So the idea there was to actually have a very local code like this, instead of having to write a
yeah,
function next to that dispatch and so on. So yeah.
yeah. And now where do we see constant expression coming into here?
Well, that's not actually where you really want to. I mean, it's not the use case where you want to be doing this all the time. So one thing this thing shows is that we need to have a way to express the fact that I want to select a piece of code at compile time. So that's one way to do it. And the new way to do it will be the C++17
Oh yeah,
if
right,
const expr.
right.
And so if const expr is basically if, but the conditional you pass to it is supposed to be something like, okay, if this is true at compile time, you compile this branch and you forgot the other one, and the other way around if it's false. So it's like a if, except the branch that is not taken, it's just discarded.
So the whole thing then becomes this example on
on
20,
on the slide
on slide
afterward, I
20,
think.
yeah.
Yeah.
So instead of having the select template which we previously
Yeah.
saw, you just have one lambda which uses if constant expr
Yeah.
to see if it's not a trivial, and if it's not a trivial, then we call construct on, in this case it's e.
Yeah. Yeah.
Or just
And done.
execute any other function in this case. So yeah, that's another big example where C++17 makes things easier. Enable if is a really great thing and has brought a lot of nice things to C++, but the constant expr if constant expr is much better and easier.
Oh yeah.
way to
it's
do it.
exactly what we wanted enable for. I mean, if this is true, do this. If not, just just forgot about that. And it's also get around a slightly subtle issue. With this, if you go back to the select example,
Yeah.
uh, there is a funny thing that bited us a bit. Is that if the lambda you select in between is not polymorphic, that the type of the parameter is not auto, but it's a concrete type, it gets compiled all the time, even if the selection won't make it usable. So you may end up with an error because in one or the other branch you may use, let's say, like a function, a member function, or a bit of syntax which is invalid if
Mm.
the test is not true. So you are forced to find a way to say, okay, I just give you a template parameters on the lambda, so you can delay the point of instantiation of the code. Something which is completely automatic with if const expert.
Okay. So
So that's one trick you have to be careful with this kind of thing.
yeah.
But it gets better with time. So yeah, well. So and I consider that this kind of code, I got this lambda. I'm taking my elements from the for each, and
Yeah.
I decide something inside to be really far more expressive than a lot of stuff you could actually write right now. And everything is there, which is the actual point of having how to say that of having a lambda function. It makes your code more local, and it removes this tricky this tricky way of trying to know at compile time if this code or this code has to be called or not. So it's
Mm.
very it's very intuitive. I mean, I think that everybody that look at this kind of code can understand what's going on, and probably more than with the version before. Which is, I think, something that the new C++
Yeah.
standard, the 17.1, is
Yeah. If
actually
we
pushing through.
this is what we had before. We needed to create two select functions to make this work. And this is now replaced with a single code line, and it's directly in the where you do things then, and it's so C++ 17 has a lot of improvements in that sector. But
Yep.
on the other hand, we still have to wait for a lot of ASAR. This is like years away. So it's nice to know how to do that with C++ 14.
Yeah. Yeah.
So if I jump to conclusion,
sorry.
So your point is if we use lambdas in conjunction with constant expression if, and use the full expression, or in C++ 14 the comma trick with variadic templates, we get the code generation you want.
Yes. Yes, it's actually something that we were able to make work on in a lot of situations, and it's actually the I mean, what we consider the probably most elegant way to actually say, okay, I have a piece of code and I wanted to replicate it in a given scenario, and everything is actually separated. I want a piece of code turns out to be, okay, I just need to write this lambda wrapping, okay, which can have a state, because you can actually capture something if you need it, and you can have its own interface with the actual lambda parameters. So okay, you can one way you select the fragment of code you want to do, and after that, the notion of iteration over the code fragment, it's another piece of the language, and you happen to combine two things to get your generation, and it doesn't force you to write this all-in-one template, meta counter, and selection and code generation in static function and so on and so on. So you write your code fragment, or you reuse them if you have them already, and
Mm.
you just have to think about the kind of application you want, and you just combine that, and you don't have to look around and try to, every time you look at the code, try to second guess the complexity of the template machinery. So it makes everything far easier to follow, and I think it has this interesting effect that you can actually have more people understanding what's going on,
Mm.
and actually using it, either I mean in a global way, or more locally. I mean, you can actually use that and get the correct API and code generation in your code base without having your collaborators looking at you funnily. So you can actually write codes that, let's say, will probably pass a proper code review process without being shut down for being too clever.
Yeah. I
Which,
really like
which
how the standard moves to simplify things.
yeah,
And yeah, if you talk about C++17 and lambdas and constant expression, the one thing I think which is new with C++17 and lambdas is that they can be constant expression now. So they're
yes,
actually
I saw that.
available as a calling context at compile time, as long as, of course, the lambda then has to adhere to the rules for constant expression, so for code that executes at compile time. But and yeah, so a lot of this, like the modern way to do template metaprogramming, is available in Boost HANA and Brigand, which is your TMP library.
Yeah, that's one of the library we wrote with a lot of people now. I mean, I'm the main contributor with Edward Alligand. We have a lot of contributors now. We work with Odin Orms, which happens to have his own Brigand-inspired metaprogramming library called Quasir. I think that's the correct way to pronounce that. There is a lot of
Yes.
discussion right now about how to actually get a template metaprogramming library up and running into the new ecosystems. So yeah, we worked on that for different reasons. The old MPL, as good as it was pre C++11, was starting showing its edges, especially with respect to the new standard. So we needed a smaller part of MPL, but we needed to be like probably 10 times faster.
Mm.
And we also were actually running into cases where the sizes of the type list or whatever we wanted
Mm.
to manipulate started to be too big for the MPL to handle. So we mulled over that. We found out about a bunch of articles, the one by Eric Niebuhr about Meta, the one
Yeah.
by Peter Dimov about MP11, and we go like, oh snap, that's exactly what we need to be doing. So I would say that the notion of having our own properly built C++11 template programming library started on. So we use a lot of tricks I speak into these slide sets into Bragant, using the pack operator expansion to write meta functions that does not depend on the size of the number of types, and so on and so on. And the small tools like this select, and moreover some others like this are also present into Brigand, because we found out it was a cool place to have them, because it was something that helped you bridge the gap between whatever you're doing at compile time, and ended up doing it at something at runtime. So that was a cool place to have all of that.
Mm.
It started quite modestly, and we keep adding things since now. As soon as we have different needs, or people came in and want to contribute, so it's growing. It's growing right now. So
Okay.
yeah. And
So
if you didn't saw it, you could actually have an hour long discussion about how to do metaprogramming right in C++. If you want to watch yesterday's
Oh yeah, I watched part of that.
yesterday's CBP chat,
Yeah.
So
Yeah, that was interesting, but also I think that Odin does a lot of interesting work there, and I'm happy that he's at C++ now, so that all those heads can stick together and have a discussion on that live.
yeah.
But I find it like interesting that most of the day-to-day users don't have the everyday interface to this.
Yeah.
So
and it's actually a good idea to not having to deal with that on a daily basis. Yeah.
But on the other hand, it gets usable by libraries like Brigand and HANA, and you as a user you're getting exposed to more and more libraries which use this, like for example your library for SIMD, for parallelism on the processor.
Yeah.
So I heard that this is in review for Boost soon.
Oh yeah. So it was quite a recurring jokes on the Boost IoT channel is that okay, will 2000 something will be the year that Boost SIMD is actually proposed to the library. So we spent a lot of time last year trying to make it actually happening. Boost SIMD is actually something we extracted from a closed source product that we wanted to share back to the community, and we worked quite a bunch of time with let's say with the Boost higher ups like like John and Michael Kess and all those guys to make it happen properly, because I know that a review is something that is actually complex both for the submitters and the actual reviewers, because you end up jumping in a very complex code base, and you have to get an opinion on that. So we worked on that for basically this since CPPCon 2016 now, and we played around all the issues about scheduling and whatnot, and how to actually make it so it happens to be let's say appealing to the community. So it's gonna be happening on April 15, if I'm not mistaken now. So it's very soon. So the library itself is already up and running. You can actually jump over GitHub and play with it. We will probably have a special release just for the review, so everybody is actually looking at the same code base in time at the same time. Yeah. So yeah.
What's the requirement for the compiler then?
Oh, that's another part that we wanted to be both pragmatic and let's say optimistic. So it's C++11 library. For different reasons, mostly because as we saw into this talk and what we discussed before, it actually helped us getting where we wanted to be, and the benefit of that was tremendously bigger than trying to retrofit it into a C++ 2003 library. But in terms of actual actual compilers, I mean, I think that we support quite a large subset of them. So, I mean, it works with GCC 4.8, which starts to be quite old right now. It works with Clang 3.5, and the only point where we need to be a bit more, strict is Visual Studio, that we requires not the latest version, but the one before. So it's 2015 now. I don't remember. I mean, their numbering of version is so confusing. So but not the most recent one, the one from before. So it should be okay. And we try actively to keep that as much as we can. We were almost having the support for 4.7, but the changes were actually having bad effects on the performances on the other cases. So we just cut at 4.8, which is, I don't know, how old is 4.8 now? I mean, it starts to be...
Are people still using GCC 4.7?
Yeah.
Do you support Visual Studio?
Yeah, we do. We do.
Okay.
We do. Not the latest one, the one from before. So that's probably 2015. So it's CL version 18 something. I don't remember the exact numbers, but yeah, it works on Visual Studio. It still has some quirks. We have a very active topic about ensuring that Visual Studio code generation is as good as the other compilers. But we are getting there. So it works, and in some cases we even have very good results. And it works also in terms of the we didn't have to compromise the API to fit what the compiler was supporting. So that was quite a win for that.
Okay. I think with that we're through. Do you have anything else?
Well,
To add?
we are probably we are probably gonna make a talk later this year, probably at CPPCon, about exactly not exactly what I spoke about at IMBO, but something about help me. I want to use C++17, but I'm stuck with insert compilers, and try to go over all the tricks we accumulated through the years to say, okay, this is a proper way to emulate these features that looks very cool, but you're stranded with the version before or two versions before of the standards. What could I do? And so we can actually go through comparing these things. So that's something we really want to push forwards later. I also welcome everybody that wants to participate to boost SIMD review to do so. We really appreciate the community times on doing this. So please come and criticize us. We are pretty much open to this. I really wish it would be a success, because I think that's something that is actually required right now in the language. And I think one way to move on this issue is actually to, again, like it was back in the day, show through a boost library that it's a sensible interface that solves a sensible issue, and so we can work on that later. I will probably discuss all of this at some, C++ standard meeting at some point, and so on. And yeah, the other part of what we say during the talk, but which was probably a bit afterwards, is the cool news is that the standard committee study group, which was SG7, which was on reflection, was renamed recently as study group about reflection and metaprogramming.
Yeah, I've seen that.
Which means that this kind of activity starts to have an actual official traction. So I will probably dig around what's proposed in SG7 and see how we can actually probably maybe propose something into this to see how we can shape, let's say, the actual standard futures of metaprogramming practices.
Okay. So looking forward to your talk then.
Yeah.
For CPPCon. And yeah, Meeting C++ is going to be announced in April, so just a few days from now.
Okay, great.
Then there's going to be some news, and yeah, this is then everything for today.
Thank you again,
for being
Jens.
on the show.
Well, thank you for the opportunity to be there.
Oh, you're welcome. You have always been, I mean, I know you since 2012, just like Rainer, my last guest. In 2012, you were like a speaker on my conference. And are you also going to be at C++ now?
Unfortunately,